It's my pleasure to welcome you here to the 2007 July Lectures in Physics program on this very bracing Melbourne July night, very reminiscent of the Julys we used to have 10 years ago. My name is David Jamieson and I'm the organiser of the July Lectures in Physics program. And I'd like to also extend a special welcome to all our alumni who might be in the audience tonight. Now, the July Lectures in Physics have been running every year here in physics since 1968. It's one of the longest running lecture programs in the university. And can I just have a show of hands for anyone who was here at the first lecture in 1968? A special welcome to our loyal members of the audience. That's extraordinary devotion to physics. We do appreciate your and everybody's interest. It makes presenting the July Lectures very worthwhile. Our theme for 2007 is physics breakthroughs. It's been a remarkable few years for physics. There's been breakthroughs in a whole lot of different areas, and I thought it was time we gathered them together to talk about them. Tonight we're going to hear about the Large Hadron Collider, just starting to power up over there on the Swiss-French border, which will be our window on the conditions that existed at the time of the Big Bang, and Geoff Taylor will be presenting that tonight. Next week, we're going to have a lecture titled A Quantum Leap for Computers, Quantum Information on the Horizon by Professor Lloyd Hollenberg, the newest professor in the University of Melbourne. On July 20, I'll be telling you about breakthroughs, hoaxes and delusions and frauds, breakthroughs that weren't, because there are some sensational high-profile breakthroughs that I need to confess to that were retracted, but a very interesting story nonetheless. And then finally we'll wrap up the 2007 program on July 27 with a lecture by astrophysicist Andrew Milatos, Hidden Mass in Cosmic Collisions, the first pictures of dark matter, truly sensational. Now, before I introduce tonight's speaker, I'd like to ask how you found out about us. Can I ask for a show of hands of how many of you saw our advertisement in the Age newspaper? Oh, excellent. Excellent, thank you. Can I ask how many of you came because you received an email directly from the School of Physics? Wow, that's very effective, thank you. And I should say those of you who'd like to be on our mailing list, or if you're alumni who'd like to keep in touch with the school, there's some registration forms out the front door where you can sign up for our regular emails. And while I'm asking you questions, can I also ask you to switch off your mobile phones at this point? Thank you. I'll have to do that myself. Anyway, tonight's speaker is Professor Geoff Taylor, presently the head of our School of Physics here at the University of Melbourne in the final 6 months of his reign, and will be handing over to a new regime at the end of the year. Geoff has come to the University of Melbourne from originally Western Australia, from undergraduate master's degrees at the University of WA, and then went on to do his PhD at the University of Hawaii, finishing up in 1981. And presently he leads one of Australia's most important research programs, namely our High Energy Physics Research Program. He's the chief investigator on some very major and impressive grants. Geoff, could you keep that C3 for me? Just the last one over there. Thank you. These grants are titled Frontier Experiments in High Energy Physics and a support for the Australian High Energy Physics Program. Geoff has a very high profile in the high energy physics community. He's a very authoritative speaker on the topic, and in just looking at the Web of Science, I see that Geoff has already had his name on 25 papers so far in 2007 alone. And just to give you a flavour of what it does, it's hard to compete with Nemo there. The title of some of his recent papers, a Dalitz analysis of three-body Chalmers V0 to K0 pi plus pi minus decays. So Geoff does a lot of charmless physics. Evidence for D naught, D bar mixing. Measurements of charmless B decays to eta, K star and eta rho. And I'm sure if you approach him after the lecture, he can give you some more details on those very interesting topics. But ladies and gentlemen, Professor Geoff Taylor.
Well, thanks very much, David. I should point out that the fraudulent experiments are not, and hoaxes are not from David, they're from other people. So who has heard the expression Large Hadron Collider before? Okay, excellent. Well, particle physics is what this talk is about. That's my field, and I thank David for highlighting the very interesting titles of some of the papers that we put together in our group. What we're talking about now, though, is not those papers, which is what is going on in current experiments. We're preparing for the next generation of particle collider experiments in Geneva, and that's what this talk is going to be about. Large Hadron Collider is talking about an accelerator, a land-based accelerator, an earth-based accelerator, a piece of equipment that has nothing obvious to do with the Big Bang or with astrophysics, but I hope that by the end of this talk you'll see that there is in fact a very strong connection between the two, and in fact it's one of the most beautiful things in physics in these modern times. So what is high energy particle physics? What are particles? Why do we need high energy? What is the connection with cosmology, with the Big Bang? And if we're talking about breakthroughs, what is the breakthrough that David is hoping for, so that this is not recorded? And when will that discovery be? Well, we know from quantum mechanics that particles at the atomic scale or smaller have neither particles nor waves, but have qualities of both. And this has been known for nearly a century now. Quantum mechanics comes into everything around us, all the electronics that we're used to, practically everything in the household today to do with electronics is based upon quantum mechanics. The expression which was really quite astounding in particle physics was relating a particle nature of these atomic scale particles to a wave nature. And it's most clearly highlighted in the expression by de Broglie relating a wavelength to a momentum. So right from the first slide, you'll have to bear with me with an equation. So this is very important to get started. The wavelength of a particle, something which we might consider to be something like a billiard ball, like an electron or some other atomic particle, is related to its momentum, and it's related inversely. So if we have very, very high energy particles, their wavelength is very short, their equivalent wavelength. Now, you've all heard of electron microscopes. You know that we make use of X-rays for probing, electron microscopes for probing down to very fine scales. The reason that the electron is used is because it's easy to make a high energy electron. And the electron wavelength is short. And why do we need a short wavelength? Well, I've written it here. If we want to resolve small things, if we want to look at small features, if we want to look at tiny scales on a butterfly wing, you can't do it without going down to finer resolution, to finer wavelengths, shorter wavelengths. So electron microscopes work getting down to the atomic scale because the energy of the electrons can be made high. And so this relationship is absolutely essential for high energy physics. That's why we do high energy physics, is so that we can get to look at things on the smallest scale possible. So the atomic scale, the size of atoms, requires energies of X-rays, keV and hundreds of keV. You get down to the size of the nucleus, which is 10,000 times smaller than the whole atom, just this little piece in the middle. We we need to get up into the hundreds of millions of electron volts, where an electron volt is the energy, basically the energy that an electron is given by a single battery, by 1.5 volts. This would be hundreds of millions of those batteries together. So in order to have studied the fact that atoms are made of an electron cloud and a tiny nucleus in the middle, energies of particles to probe those atoms had to be of the order of MeV, up to hundreds of MeV to see the structure of the nucleus. If we want to go smaller, to look for finer and finer details, for more fundamental particles, we've always had to push to higher and higher energies. So high energy particle physics is, we use big machines just to get the particles down to very fine wavelengths so that we can see what stuff is made of. Just to give you some scale of the sizes involved, here we're going from the size of the universe down to very, very small particles. So the virus or a cell is of the order of a micron, a millionth of a meter, 1,000th of a centimeter. An atom is this 10 to the minus 10 meters, 9 zeros 1 of a meter. Proton, the nucleus is another factor of 1,000 smaller, 10,000 smaller. And on this side here is the scale of the type of device we have to produce in order to be sensitive to those sizes. And what we're trying to do in particle physics is push in this direction to look for very finer and finer scales, and so we have to go up higher and higher in energy. And the Large Hadron Collider is the next frontier in the energy scale. There's a little diagram on the side with a picture of the size of the atom, the nucleus, and the particles inside the nucleus. I have more to say about that in a second. One thing which has been important time and time again in trying to understand and push back the frontiers of physics is to use patterns. And there wouldn't be too many people in this audience who wouldn't know what this pattern represents even without being able to read the fine print. This is the periodic table, or the Mendeleev table of elements. And through the chemistry of these elements, the elements in the rows have, in the columns, have similar chemistry. It's due to the outer electrons, the valence electrons of these materials. And it's true in most of these rows, it's a bit more complicated towards the middle here. So the symmetry of the chemistry, which was the this table was based upon, was able to put hundreds of elements together into a pattern. And that pattern, of course, now corresponds to the atomic number here, the number of protons inside the nucleus of these atoms. So symmetry, this is a very simple example. It's an example that you all know so well, you probably don't even have to think about it as symmetry anymore. But it clearly is. This is the sort of pattern which is made, given us really very strong tools into understanding the matter around us. So, as I said, in order for Rutherford to have seen that the nucleus is the centre of the atom, that it wasn't somehow distributed over all the matter, that there was a very hard core right in the middle, much smaller than the entire atom. They had to use alpha particles from that natural radioactive decay, which have millions of electron volts of energies to try and probe those atoms. As accelerators, which were artificial ways of producing these high energies, were created in the 30s and beyond, in order to go down to probe the matter more deeply, we ran against another issue, which was also kind of part of the physics of the first part of last century, and that is this relationship between energy and mass, and that mass is a type of energy. And so how does this affect us? As we go up in energy to try and make our wavelength small, okay, we want to make our wavelength associated with these particles very small by going to high energy electrons or high energy protons, we start to get into a regime where the energy is so large that some of the energy can be turned into mass. And we start creating particles at the same time that we're trying to probe what matter is made of. And that has two sides to it. It has a good side to it. We can create particles which are difficult to find in nature, because they're very short-lived, or they don't survive and don't hang around very long. That's the good side. We can actually discover particles which are created in high-energy interactions in the centre of galaxies or the centre of stars. But the bad side is, as we go to high energies to try and probe the matter that we're trying to study, the energy in those, as those particles interact, gets converted into mass, and we create particles. In this case here, this is a picture from a bubble chamber, the first device that I ever worked on, and you'll see these little squiggles starting from a point, and there's quite a few of them all over the place. There are these squiggles which go in one direction and squiggles which go in another direction. Those squiggles are electrons and what was discovered in the 30s as well, anti-electrons or positrons. So when energy in the form of photons, particles of light, interacts with the liquid in the bubble chamber, sometimes those photons convert into particles. So they take their energy and they can get converted into mass. And all of those little V's, little squiggly V's, are where a piece of energy, a photon of energy, has created a particle-antiparticle pair, an electron and its antiparticle positron. I want to highlight that because, as I said, there's two issues going on here. In fact, what we want to do with very high energy accelerators is to create particles which decay away so quickly that they don't exist on Earth now. But we want to create them because that was part of the palette of particles that our universe was created from just after the Big Bang. That's what we're going to get on to. So high energy, short wavelengths, and creates particles. And in the more modern, in the high energy regime, this is the sort of thing that we're going to be up against. This is actually a simulation. Right at the centre there has been the collision into and out of the board of two very high energy protons. The protons, the energy of those two protons has created hundreds and hundreds of particles. And those particles have come out. So this is a really dramatic exhibition of energy being converted into mass. This is exactly the sort of event that over the next couple of years our students will be trying to disentangle from other types of events. So as energies in the accelerators increased and the big accelerators, the age of big accelerators in the 50s and 60s took over, there were all sorts of reactions like this taking place. Most of what you see on here is not very interesting. Most of what you see is a charged particle, high energy charged particle going in the bubble chamber and out the other end, not doing much, just ionizing so that you can see the track. But occasionally things occur. For example, over here, a track has come along and then it's hit a proton inside this bubble chamber and it's created 3 or 4 particles here. And it's created another particle-antiparticle pair which points back to there. This was the sort of evidence that through the early 60s led to the particle explosion, the zoo of particles. Hundreds of particles were discovered over the period of a decade. And so the cleaner in the cyclotron at Berkeley, particles sweeping them up. It was just a bonanza for particle production. And in fact, it was for a while to try and understand where all these hundreds and hundreds of particles came from was a major block for the understanding of matter around us. And there were all sorts of theories going on, many of which just fell by the wayside as we progressed. And the progression, again, made use of patterns, of symmetries, of looking for combinations of properties of particles to try and do the equivalent of the periodic table, but at the particle level. And the details of what these parameters are, it's not the atomic mass and the atomic number as on the Mendeleev chart, but putting various properties of these particles together, they form patterns. And that the idea of patterns immediately led to or the evidence of patterns immediately led to the idea that there was something below that. Just as there are protons and neutrons which lead to the Mendeleev chart, this symmetry here indicated that there was something more important going on. And that more important something was the quark model, the quark model. It was developed through the 60s just to try and find a solution to that symmetry, to those patterns. And as we know, over the last couple of decades, in fact, the quark model has become very, very precise, and with the addition of further discoveries. And there's an interesting few issues with the quark model. It comes in 3 different families. In fact, there's 2 quarks in each family, and then down here there's another set of particles called the leptons. You all know the electron is in atoms. And in fact, those 2 quarks in that column, the up quark and the down quark, they make up protons and neutrons. So with the electron, protons and neutrons, everything that is in this room is pretty much accounted for. The low energy, quiet Earth that we sit on is basically all made up of protons and neutrons, which are made up of these guys, with the electrons around for the chemistry. These neutrinos are a partner to the electron. They don't have any charge. And in fact, the atom is held together by the electromagnetic force. So neutrinos don't participate in chemistry. They're not sitting around us. However, they are created in nuclear radioactive decay, and they are created in fusion reactions at the center of our sun. So in fact, while I've been saying there's nothing but those 2 quarks and an electron in this room, millions and millions and millions of neutrinos have passed through us, each of us. They pass through without doing anything because they don't have a charge, but they're actually rather important because there's so many of them that they contribute to the mass energy of the universe. So we could probably describe everything, we didn't go any further, with the one column. What are these other columns? Well, the other columns are particles which exist. They don't exist for very long, and they seem to be replicas of this one that we're all made of. They exist because when you can create them, you can take high energy particle beams, or you can be out in the cosmos where high energy reactions are taking place, and you can turn energy into these things as well. But because of the replication, in fact, they have a very strong predominance to decay from this column down to this column, and from this column down to this column, down to this column. They decay, they change their state very, very quickly through the weak interaction. So, although nature has put these extra families of particles in, they're not stable, and they don't contribute anything to the quiet world that we live in. They do, and they have contributed enormously to the more energetic parts of the universe, and certainly at the very early phases after the Big Bang. So this triplet of families, we don't understand why. We have a few ideas, but we have no real definitive idea as to why those replications occur. We don't know why this one was made and why this one was made, but we do know it's part of nature. And their properties are very similar. The big difference between this row and this row and this row is just their mass. And mass is quite an important part of this topic, of this talk. So understanding where all these things come from is quite important. Here is on the blue is what we call force carriers. There are 4 known forces of nature. Electromagnetism, which in centuries gone by was considered to be 2 different forces. There were magnets and there were electric forces. We know now that they're just manifestations of the same electromagnetic force. And we explain them in the language of quantum mechanics or in quantum field theory by the exchange of photons, or particles of light. So charged particles interact by the exchange of these photons. Similarly, these quarks, interesting thing about quarks is that although we can create them, we can measure the particles that they're sitting in, we never see them by themselves. They've never been observed outside of a state where there's 2 or 3 quarks involved. Nevertheless, they exist. So why are they held together? Well, they're held together by the strong force. It's another of the forces which holds together the nucleus, but the strong interaction is really the interaction between these quarks mediated by the exchange of gluons. You know? That's what they mean. Glue stuff together. This whole thing is called the standard model. David said that charmless and strange particles and so forth. I think there was an era when people were a bit more gregarious in the names they were choosing. In the 70s, it's standard model and gluons. So these things here are force carriers. And down here we have the Z and the W. And they were discovered in the early 80s. These particles mediate the radioactive decay, beta decay, the decay which creates at least some types of radiation. So absolutely essential again that they exist because of what goes on in the centre of our sun, for example. It makes use of these guys. In the last, or I guess from the late 70s on, there was another major discovery in this so-called unification of forces. If there was someone here living in the 19th century and early 19th century, you had a magnet and you had a charged up plastic rod that you've been rubbing on some poor dead cat's fur, like we do in first year lectures, the 2 forces would not be considered to be the same. We know now that they are, and that magnetism is just due to circulating charge or spinning charge. We know that that's the case. So electromagnetism encompasses both electric force and magnetic force. In the last 20 or 30 years, it has become very clear that in fact these guys participating in the weak force, it is just another manifestation of the electromagnetic force. So we call that, those things have been combined into one theory called the electroweak theory. So we've already found that this guy and these 2 guys are basically responsible for electromagnetism and weak interaction in a unified description. One theory can describe all those reactions. So it's a beautiful model. This is the stuff of the electroweak unified standard model is described by that little box. Of course, there's a bit more mathematics which go to describe the interactions that they participate in and the types of forces that these things operate under. But that's it. Not hundreds and hundreds of particles. That's it. And it has been incredibly successful. Let me just go back to this thing I highlighted before, and that is the mass of these objects. The electron in these units of giga-electron volts, 10 to the 9 electron volts. The mass of a proton is about 1 giga-electron volt. So this thing here is 0.0005 times the mass of a proton. The muon is only 10% the size of the mass of the proton, so it's much closer. 20 times higher than 200 times higher than the electron mass. And then its next electron, the heavier, the grandfather of the electron, is 2 times the mass of the proton, 1.8 times the mass of the proton. The neutrinos are even more awkward. Practically 0. Not quite 0, importantly not quite 0, I won't be talking much about them today. But so it goes from a tiny mass right through to something twice as heavy as the proton. On the quarks side, we have a similar issue. From a few thousandths of the size of the mass of the proton, right up to the top quark having about 200 times the mass of the proton. So although we've got a very neat picture of these families, we know those particles exist. We know that matter, right from the beginning of the universe, was created from those objects. And the only reason that there's only one family left for us is, fortunately, because the Earth, the universe quietened down so that we could evolve. A big problem with trying to make that nice symmetric model is that there is a huge range of masses here. And in fact, the standard model, the beautiful standard model, which has been tested time and again over the last 2 decades in all sorts of areas, and is accurate down to 1 part in 1,000. You can get very, very accurate experiments. It doesn't have anything to say about the mass of these objects. So it would prefer, would be happy for all those objects to have the same mass. So that's our first little quandary. And similarly, the mass of these, of the W and the Z, these weak carriers, are something like 70 or 80 times the mass of the photon. Mass of the gamma of the photon is 0. So although the patterns are beautiful, and so far we haven't been sensitive to these things playing a direct role to upset the standard model, we have to explain these things. So there's some data which is very, very precise data saying that there really are just 3 of those families. If there were 4 families, the data from the LEP experiment at CERN from a decade ago followed this green curve with very small error bars. And that's for 3 neutrinos, for 3 families. If there were 4, the data would have to follow this pink line. If there were 2, it would have to follow that pink line. Very, very precise data showing that we're not just, it's not that we've just missed a few, not that we're miscounting, there are 3 generations. This is the other thing about quarks. We don't see quarks. I can give you an electron, I can give you a proton, you can have a proton in your hand, a bottle of hydrogen is made up of protons and electrons. I can't give you a quark. Quarks don't exist by themselves. So how do we know they exist at all? It could just be a nice mathematical game. It's not a mathematical game, and this is how we see them manifesting themselves in an experiment. Our proton is made up of some quarks, the other proton is made up of quarks. When we bang them together, they don't just bang together like big squashy objects. Every now and again, if you hit them very hard, the pip in this one hits the pip in this one, bang. Very high energy interactions, large scattering. So why can't you hit them hard enough to knock a quark out? Well, the interaction between those 2 quarks is such that it drags energy with it and creates particles out of that energy. So in the experiment, we don't see 1 quark, we see a bunch of particles called jets. So as these pips get knocked, hit them as hard as you can to try and knock them out of the nucleus to identify your single quark. It drags energy with it and through those interactions, through those strong gluons, and then we turn energy into particles again, and they get pressed into these jets. But those jets, the direction of that jet tells us the direction of the pip that was hit. One little nugget inside the proton, one against the other. And we make use of the direction of these things as a whole to tell us how the scattering is going on. We see the quarks bang into each other. It's just that when we're out in the experiment, we can't isolate them. So the standard model has been tested. It's been tested at low energy on benchtop experiments. It's been tested at the highest energy experiments in laboratories that we can look at. It's been tested in cosmic rays. It's been tested all over the place. Every time the test is made, it's consistent with the predictions of the standard model. The standard model has been so outstandingly successful. It really is unrivaled. But there are shortcomings. The mass issue, and there are other issues. There are too many parameters. Scientists like to think that there is some sort of simplicity behind everything. We look for symmetries, we look for patterns, and if we need lots and lots of parameters to describe those symmetries and patterns, then we've taken the suspicion that in fact we've missed some higher level of symmetry, some higher level which is creating the requirement for too many parameters. So we're looking for something beyond the standard model in order to remove some of these uncertainties. Now I'm going to switch to some aspects of astrophysics and cosmology. I'm not an astrophysicist nor a cosmologist, but the two fields of looking at the very smallest properties of matter and looking at the very largest, looking at the furthest distances, have actually come around and are connecting together in a very, very significant way. First of all, just to remind you of the evidence that we're living in an expanding universe. There's a few things that you would require to see if you were living in an expanding universe. And one of them is that if I'm looking at a galaxy over there, if the universe is expanding, I should see that galaxy receding. And similarly, if that person in that galaxy is looking at me, he'll see our galaxy receding. So first of all, there's no direction involved here. This is a completely homogeneous universe. Secondly, if it's not just one galaxy moving away from us, if it really is a whole expansion, there should be, if the whole universe is expanding, there should be no preferred centre. And that's what this diagram here is supposed to try and show. If what we've got on here is different parts of space, so along here, this is the galaxy. Up in the vertical distance, the vertical direction is time. So when I'm just looking at one particular time, I follow one of these lines along the bottom here. And these points where that intersects the bottom line, where that intersects the bottom line, that one, they correspond to galaxies. So I'm looking from my point A here, I'm looking at galaxy B, time 0. And I'm seeing that galaxy move away from me. Now, is it just that one galaxy, or is the universe really expanding? Well, this guy will see the galaxy, if it's really expanding some distance away from him, moving away as well. And this one, if the whole galaxy is expanding, we'll see this guy here also moving away. When we look at this guy going too long, he finds that the distance that this galaxy over here has moved twice as far in the expanding universe. So the further he looks, the faster the relative motion seems to be. So the further you look at an expanding universe, you should see that object moving away from you faster than the closer ones. And similarly, if I'd started on point B here, then there's no centre, there's no preferred point. You don't need a preferred centre for this to work. So this is in fact the analysis that was carried out by Hubble a long time ago. And this is some more modern data by looking at a certain distance here in this weird unit of megaparsecs. This is a large distance, and then this is the velocity of these things going away from us. The velocity is determined from the redshift. The redshift, or blue shift, is the train whistle effect. It's the Doppler effect. A train coming towards you blowing its whistle, very high frequency as it goes away, and the frequency changes to galaxies coming towards us, the light on the spectra of those stars is shifted to the blue because it's high frequency. Galaxies going away from us is shifted away to the red, the low frequency. And that's how this velocity is determined. And this data here shows that the further away you go, it just rises linearly with speed. Linear is important too, we won't get into that. But the further away, the faster the galaxy appears to be moving away from the North Star. This little dot down here, in fact, corresponds to Hubble's data back in the 30s. And looking back on it now, you wonder whether he found what he wanted to find or whether that was really it. But it's very clear. Oldest paradox of skip. Okay, so there was, from looking at redshifts, right, there was pretty strong evidence that in fact the universe seemed to be expanding. And then in the early 60s at Bell Telephone Company in New Jersey, they were trying to use microwave signaling with a massive antenna. They wanted to be very low noise antenna. They couldn't get the noise down. There was this hum of noise which they tried everything. One stage they found some pigeon poo in there and they got rid of that and they changed their electronics. Couldn't get rid of it. And in fact it turns out that background noise, that background hum of microwave signal is the glow, as we know, as we interpret it nowadays, of the Big Bang. So this is the glow of fire which took place 13 billion years ago, and now is because of this redshift, because it's happened so far away and so long ago, and the expansion of the universe, what was very hot in those days is now much cooler and is seen in the microwaves. There have been probes since that, COBE and WMAP, which have taken the fact that there is this microwave background and in fact mapped it out with very high precision. WMAP in particular has extremely high precision. And so we have a very good idea about the temperature of the corresponding temperature of the microwaves now, and we use that to help determine the age of the universe. So the expanding universe, and in particular with this microwave background, led to the idea that we must have come from some beginning, some Big Bang, something occurred long ago which led to the expansion of the universe. And those of you who pump up tyres in the morning, cold mornings for good when your tyres flat, some days are so good. As you pump up the pressure, raise the pressure inside your tyre, the valve gets very, very hot. If you let the valve out, let it expand, it does work, touch the valve and it will be very cold. So the expansion of the universe itself causes this cooling. By going backwards in time, pumping the tyre back up and trying to figure out what it was like backwards in time, you know that it was hot. So it's a hot Big Bang model, and 15 billion years ago, the temperature was not even comparable with the centre of the sun, much, much, much higher. And so then we immediately start to talk about the reactions which are taking place by the molecules and the atoms of the universe just after the Big Bang were high energy. So they were rattling around like the gas in this room is rattling around because of the thermal motion of the atoms. Low energy. Back then, very, very high energy. So all of this stuff that we know about from the standard model, all of these interactions were actually occurring back there. We weren't living in a nice, low-energy, calm environment that we have now. There were heavy quarks, there were top quarks, there were bottom quarks, there was the whole mass of those three generations being created and bumping into each other in the very early universe. So in order to understand that very first phase of the Big Bang, we need particle physics. So to understand the universe at its largest scale, we need the physics which has come out of studying matter at the smallest scale, and vice versa, as we'll see. So if we look at a picture of the history then of the universe, there's a couple of features which I won't say much about, but we're living out here, the thinker. Don't get much time for that now. If we look backwards in time, we're also looking further away. If we go backwards in time to say a few 100,000 years after the Big Bang, 200,000 years, 300,000 years or so, it had cooled enough by that time for the electrons which were rattling around and the protons which had formed to come together to be neutral atoms, neutral hydrogen. So before that, it was all charged. The energy was so high that atoms couldn't stick together very long. A charged atmosphere, high pressure charged atmosphere is called a plasma, and light doesn't travel through a plasma. So if we use optical techniques to look backwards in time, we can't get beyond here. And it's in fact whatever state the temperature and distribution of the energy thermal energy here, as this is what has contributed, this is what we're seeing now in the microwave background. It's that, whatever happened at that time there, having cooled through expansion, having been redshifted down to a few degrees. But there it was very hot. So 3,000 degrees. Okay, so that's atomic physics. That's nice. We can do that here in the lab. It's not so difficult. We need to go back further to try and understand what happened. And in fact, now we're getting into the regime of nuclear physics, where the energies were so high that they're MeV, or higher interactions. So nucleons existed, and they bang around with the nuclear force. Back here, at a certain point, not even the nucleus stays together. So much energy in those collisions that it's just quarks and leptons and neutrinos. And so this is a regime that we can only understand by trying in the lab, in the particle physics lab, to see the sorts of interactions you should expect. There's a funny little thing here called inflation. And this is to do with the fact that the universe is rather smooth, but it has lumps. It's a mixture of smoothness and lumps. And in order for the thing to have this gross distribution that we see right now, there had to be a period of very rapid expansion so that the lumpiness isn't destroyed. So the Big Bang model is pretty well established. You'll see in some of the less reputable journals and newspapers around the place trying to stir the thing up, and we always try and look for new models or glitches or problems, chinks in the armour of these models. The Big Bang model is well established. So what's the big deal? Well, there's been a few very important discoveries in astrophysics in the last couple of decades, which have, when pulled together, give us a very stark contrast in the picture of the universe that we've had from if we just start with the standard model of particles. One of those is the fact that there seems to be a whole bunch of dark matter. Dark matter means doesn't shine. You might say, well, rocks don't shine. Is it just rocks? No, it's not rocks. It's some kind of matter that we don't know about. We know that it exists because of several things. If you see there are these crescent-shaped objects here, and you can sometimes see rings of these crescent-shaped objects. This is gravitational lensing, and it means that between the object where the light was being emitted and where we're observing it, there must have been some large masses. And those masses cause through the gravity effect on the light, cause the light to bend. You end up with some characteristic lensing, lensed images. And that's very nice in itself. It's very interesting physics in itself. But the key thing that I want to drag from that, and that people have dragged from this data, is that there is a large amount of matter between us and these distant galaxies that we don't see. We only see a manifestation of it here. It's not shining stars. It's not bright galaxies. There's dark matter in there, which has gravity, but that's all that we know about. The other thing is a bit more complicated, but it's not too bad. Everybody knows about gravity, and in fact, gravity doesn't change much from here to the top of the mountain, but it does change a bit. And in fact, if we move away from the Earth, the gravity falls off like 1 over the distance squared, 1 over r squared. So if you have a galaxy which is being held together by gravity, and you look at some stars around the outside of that galaxy, and you see how fast they're going, if they're still attracted to that gravity, you can figure out at the position of that star what the force of gravity is. And so if you have a look at stars further and further from the center of the galaxy where the mass is sitting, you should see the velocity falling off corresponding to the gravity force decreasing. This is what we call a rotation curve. So the object's bound, just like a satellite bound to the Earth, the object's bound to the gravitational force of a galaxy gives us an indication of how much mass there is inside the orbit of that object. And these plots show that as you go further out, the force doesn't fall off. And that's interpreted as the further out you go, you're not leaving the matter behind. There's a whole bunch of dark matter outside of the shining galaxy. And this is a very important piece of evidence for the fact that there is matter out there that we don't see. It has gravity, and it's continuing much further than the bright part of the galaxy. So we know about dark matter, and there are more surprises, which I won't go into much detail about. But there are. I showed the picture of the W map, looking at the cosmic microwave background, and the colour code corresponds to very slight temperature changes. And those experiments are so accurate that they can analyse the ripples on top of the 3 degree background, and it's like 1,000th of a degree over 3 degrees. It's very, very small. They can analyse those and make analysis of those ripples. And the ripples tell you about the material which existed 300,000 years after the Big Bang. And more importantly, more recently, with an Australian group as well as a US group, have found that the expansion of the universe seems to be speeding up. Now, if we take a model where you have Big Bang, space, and the material expanding from the Big Bang, the only thing that you've got left after that explosion, in our normal way of thinking, our simple thinking, is gravity. So the expansion may not slow down very much, but gravity will eventually just, it's like throwing a rock up into the air. If you throw it fast enough, it'll leave the Earth and won't even become a satellite. If you don't throw it fast enough, it'll eventually slow. If it's just the right speed, it'll go into orbit. But if you don't throw it fast enough, it'll come back down. Gravity will slow things down. So you expect, if it's just a big bang, bang, and that's finito, that at some point the acceleration, the expansion will slow down. It may not stop, depending on how much mass there is. But it's speeding up. The only way you can have it speeding up is you've got some extra force pushing it out, some extra pressure, something going on. And we don't know what dark matter is. We have no idea what's causing the expansion of the universe to speed up. But it goes under the guise of dark energy. It's a negative gravitational pressure. It's a weird thing that pushes, continues to push well up the Big Bang. Very surprising. So now we have a standard model of cosmology with all that data together, and that's a facetious note, but a twist to have cosmology as a standard model. 2 decades ago, cosmology was just one step away from religion, and not a very big step. And so now we have not only a model which seems to fit the data, but it's a model with numbers on it, not just orders of magnitude, but very precise numbers. And the really killing thing for the particle physicists is that all this universe, this is the stuff down here that we know about. This is the stuff which the standard model describes so well. This stuff we don't know what it is. And this stuff we don't have any idea what it is. So, cosmologists and astrophysicists have discovered for us, but they're not going to be able to tell us what it is either. We somehow have to, and we think in the coming few years we're going to have something to say about dark matter. This stuff here is much more difficult to understand. So, beautiful Mendeleev chart, beautiful three generations folding into this to make protons and neutrons, but we also know that there are these other particles who, unfortunately, that's all it explains. Just a little bit there. So, let's have a look at some of these unsolved mysteries. The universe is accelerating. Not quite sure what it's all about. Einstein, in fact, put a constant into his equations, and later in life said that was the biggest mistake he ever made. Looks like his biggest mistake is exactly what the universe does have, but we're not quite sure what drives it. no antimatter as well. One of our experiments, the experiments that David was talking about, is up in Japan, not in Geneva, and we're trying to understand why the universe that we live in now is basically all matter. There's basically no antimatter in this universe. Whereas in the Big Bang, with all the interactions that we know about, we are very sure that at creation there was equal amounts of matter and antimatter. What is dark matter? The experiment I'm about to describe will have something to say about that. And finally, what is the origin of mass? And that's the driving measurement behind the experiments we're talking about now. And I'll get on to the Higgs mechanism in a bit. There was a book which was presented to after a big study a couple of years ago, looking at the biggest questions we have to answer now, and they follow what that last slide is talking about. Undiscovered principles and symmetries of nature. Try and see where 3 generations come from. Try and see if we can simplify things by going to higher symmetries. What is dark energy? No idea. And in fact, some of these things can be solved by discussion of extra dimensions. We live in a world that we believe is 3-dimensional. It has, I can walk both directions sideways and forwards, I can go up a stairway, and the 4th dimension is time. In fact, many of the not so outlandish ways of describing some of these problems say that we're embedded in a higher dimensional space. Maybe there are 8 dimensions of space, maybe there are 10 dimensions of space. We're just not sensitive to. And that's a really big question. It's a really interesting thing to try and consider. I mean, an ant on my desk table or on an orange, 3-dimensional object, we know it's a 3-dimensional object, it's an orange. But an ant walking along that surface doesn't see it as a 3-dimensional object, sees it as a 2-dimensional surface. If we let the marker come around and find that, yes, it's been there, so it must be a closed space. Maybe we're just not sensitive to things. In fact, we don't believe that it's a big dimension like that these extra dimensions should be, but probably more likely to be very small dimensions, rolled up dimensions that we're not sensitive to. But cosmic string theory all points in the direction that maybe we should be looking for extra dimensions. And in fact, one of the predictions of extra dimensions that we can test in this next experiment we're going to hear about is that we at high energy, at these energies we're talking about, we should be able to create mini black holes. So strong gravity would be occurring at high energies, would be an indication that in fact we are just living in a high dimensional surface, a high dimensional space we're not used to, we're not sensitive to. Why are there so many kinds of particles? What is dark matter? Can we make it in the lab? That's what we're trying to do. That's one of the key things we're trying to do. Cosmic rays are things which rain down upon us, neutrinos. These are extra questions which won't be covered in this talk. The origin of the universe. Maybe that gets back to religion. I'm not sure. And what happened to antimatter? So these are the big questions in particle physics, and there are some parallel questions for cosmologists. So we're living in a world where our energy, from the Big Bang going in the other direction now, our energy here is of the order of 1 with 12 zeros electron volts. Tera electron volts. We've shown that the electromagnetic force and the weak force are basically manifestations of the same thing in the last couple of decades. And we're looking to this next regime getting closer towards the Big Bang. And because of where we are with this information coming from cosmologists, with our very, very firm experiments with very firm results on the standard model, there are questions which the standard model breaks down on when it tries to predict things in the next generation, this tera electron volt scale. The standard model is beautiful until now, but when we go an extra factor of 10 in energy, some of its calculations, some of its predictions break down. So we know something has to happen in the standard model, and in fact, many of the pictures for dark matter and dark energy also require things in this regime. So we are aiming at experiments to go to this tera electron volt regime. and that's the Large Hadron Collider. It makes use of an existing tunnel from a previous experiment underneath the farmland and airport and cafeteria at CERN in Geneva on the Franco Swiss border. And it's 27 kilometres around, so it's a massive circle. There are cows happily grazing on top. And over here, some hikers going up into the mountains. It's about 100 metres underground. The tunnel was built in the late 80s for the LEP experiment. This machine uses the same tunnel, but all the old magnets were taken out. So how do we make high-energy particles? A television screen uses similar mechanisms. You use the electric force to accelerate the electrons, and you use a magnetic force to bend them. So around here, we have it stuffed full of very high-power magnets to keep the particles in a circle. And every time they go around, there's several places around the ring where they get an electric kick. So the energy of the particles is two sets of particles in each direction, going in counterclockwise directions. Each particle beam has an energy of 7 times the tera electron volt, so 7 trillion electron volts. And at two places in the ring here, they are made to collide head-on, and their energy can be converted into whatever particles exist. So the LHC tunnel, this is what it looks like, but it's all stripped out and new magnets put in. These magnets were the most expensive part of the whole project. They're about 16 metres long, and they run at the superconducting magnets running under at 1.9 degrees Kelvin. Very complex objects, and as I said, they were the biggest part of the expense of the project, but were finally built in European industry. A lot of testing, but there was 1,800 magnets around the ring, so there was a lot of magnets of various types. Welding up, cryogenics, and many hundreds of thousands of litres of liquid helium. This was the last magnet put down a couple of months ago. It has to come down 100 metres from the top and then into the tunnel. So connected up. The Atlas experiment is out of place. This is the experiment that Australia is part of, and in those 2 points in the ring where the beams are colliding, we have to have instrumentation around them to see what comes out. So we're trying to see what particles, what matter is made from E equals mc squared, what is being created. And most of the time, not much is created. Most of the time, two protons go through, make a bit of a mess. We see them in the detector. Okay, we know about that sort of thing. That's just electromagnetic interaction. We let it go through to keep Unfortunately, for every one of those, the very interesting events are like a needle in a haystack. In fact, they're like a needle in about 10 million haystacks. We have to look at 10 to the 12 ordinary events, so 1 trillion events, 1 trillion events of that type to find the sorts of things we're looking for. So computing and instrumentation requirements are pretty important. This is the scale. This is the person down here, so it's the size of the height of a 7-story building, and it's about 40 metres long. And the reason that we have to have it so big is that the particles being created, even though we've converted a lot of the energy into their mass, they still come out with very high energy. So in order to see what they are made of, we have to we need a large area to bend them and to analyse them. That's how it looks in a 6-story building. So the sun never sets on the collaboration. In order to build an experiment like this, we can't do it with one country, not even with one region. And all the yellow countries, as the various ones, including Australia, as part of the experiment. 2,000 physicists. Can you imagine 2,000 physicists? Sounds like fun. The different types of detectors, the reason also for the complexity is because we have to discern different types of particles. Some of them are photons, particles of light with very, very high energy, like gamma rays are much higher energy than X-rays. They go through this first part, but are trapped in what's called the electromagnetic colouring. Charged particles, like the muon, that's that heavy electron, they come through, they get bent in the magnet here, we detect them in through here, and they don't get absorbed at all. So they're a particular kind of particle which goes right through to these detectors, the muon chain. Protons, charged particles, they get bent in the magnetic field in here, and they get through most of this, but then they get trapped in what's called the hadronic colouring. Neutrons go straight through, they're not charged, so we don't see them in the inner part, and they look a bit like a proton by the time they hit this part. And then electrons are also charged, so they bend, and they leave a characteristic deposition of energy. So the energy deposition of a photon and electron is the same, but there's no track for the photon. Neutron and proton is the same, but no track for the neutron. Muon looks a little bit different. We have to detect all of those particles and unravel them. So that's part of the reason for the complexity, why we need so many people and so much complexity. This is what the Atlas experiment looked like about a year and a half ago. These fantastic magnets around the thing, which was the major technological breakthrough, really. Very high performance magnets. Nothing had been built anything like it before. And this is the part that Australia was involved with, right in the centre of the detector. This inner detector. These are all silicon tracking particle detectors, which are sensitive to those electrons, muons, charged particles coming out of the interaction. This is what the real thing looked like. Make it look some nice lights, make it look like something of some sci-fi. This is one of the wheels. Each one of these pads here is a silicon detector. There were 2,000 of them made in this part of the detector, 4,000 altogether, and this is where Australia participated. We built some of these modules which correspond to the detectors on that wheel here in the basement. And putting it together, I was looking at this photograph, and I thought, well, we'd find that one. And this is where it was put into the down underground into the main detector about a month ago. So, two on top of each other. One of the things which has been where Australia is playing quite a strong role, and which has been really one of the major problems in building an experiment like this and operating it, is the computing required. When this was the experiment was first conceived back in the late 80s. The data rates, the amount of data flowing out of this one detector was about 2 times the entire telecommunications data for the world. And so we just thought, well, Moore's law, we'll just wait long enough and we'll go. And we're still putting off buying some of these computers because we're not quite there yet. The amount of data coming out is several petabytes. Are there some techies around? You would have heard of terabytes. Terabytes are a lot. Petabytes are 1,000 times more. A terabyte is a fairly big amount of data nowadays. You have hundreds of gigabytes in your home computer now, which is already a lot. A terabyte is about 200 DVDs, and a petabyte is 200,000 DVDs. So every year we'll be producing about 1 million DVDs of data on each experiment. And we don't use DVDs. So Australia is playing a role at this tier 2 level where we're just in the University of Melbourne Computing Centre and developing the tools for sharing resources right across the world. So you might recognise Stephen Hawking here. He visited the lab a few months ago, and we've shown one of these simulations of black hole production, many black holes being produced. And Stephen Hawking was responsible for discussing what was called Hawking radiation, and that is that even though black holes are black, they in fact emit some radiation. They shrink in time through a quantum process where radiation is lost. And it's determined by how big the black hole is. A very large black hole doesn't lose very much of its mass quickly, but if it's a very small black hole, because the change in gravity is very large, then the radiation process is enhanced. So the very small black holes, they disappear straight away. So it doesn't matter, you don't have to be scared that when LHC turns on, we'll all be sucked into a black hole. But the creation of these mini black holes, and they'll spit out radiation in a way which most interactions don't do. That is, with just a democracy of particles. There'll be a rash of particles coming out of these black holes if they're created. So if gravity becomes strong on the TeV scale, and in other words, if we are living in a world of high dimensions and these sorts of things take place, Hawking said that'd be great. You do the experiment, I get the Nobel Prize. So I hope I've given you a feeling for, I think, the really, really exciting moment in time for us physicists right now is that what I said before, the scale of cosmology and the model of cosmology requiring a whole set of things which we don't know what they are. We don't have any idea about what this dark matter might be. We have a few candidates, and without showing it, the experiment will be sensitive to quite a few models for this dark matter. Dark energy we're not sure about at all, but the process for giving particles their mass, the simplest process, is to assume that there exists a new field called the Higgs field. It's a scalar field which permeates the entire universe, and the particles drag through this field, the regular particles interact with the field, giving them different masses. That's the simplest model. To have a broad field through the universe is quite similar to what we would need for dark energy. It's not exactly the same, but it gives us experience with those sorts of ideas. So dark energy will be difficult. Dark matter we'll have something to say about. We really will be capable of testing and probing the shortcomings of the standard model that are expected in this regime. So something new has to happen in particle physics. We'll almost certainly be saying something about the new results from cosmology, and then just exactly what new physics there will be. There's a range of things. The Higgs mechanism, as it's called, for this broad field, may be it, or it may not be it. And the simplest Higgs mechanism may not be it either. So we know that something has to be found. And we know that something has to be found at the energy of this next machine. And we've built the machine and the detectors to be sensitive to practically, in some way, to all the possibilities. So I'm not a betting person, but if something big doesn't come out of this, I'll be very, very surprised, as will most of the world. So all the solutions postulated for these issues right now are exciting, all of them. Whether it's high dimensions, whether it's something called supersymmetry, whether it's the Higgs particle, whether it's black holes, where all of these things are going to have end up as a major revision in our understanding of the matter and the universe around us. So I'll stop there.
It's always amazing that the human organism, highly evolved for hunter-gathering and socialising in the savannas of Africa, should have some spare capacity from those complex tasks to ponder these big questions. That's very remarkable to me. So I think, Geoff, we're prepared to answer a few questions. The gentleman over here on the stairs.
Yes, it reminds me a bit of Isaac Newton. He said, I was built like a little child at the side of a river with all the great unknowns in front of me. Now, I put it to you that knowing 4% is a bit like looking at a cat and only seeing its tail. Would you agree that this means that we actually don't know much at all?
Yeah, I would. We don't know much, but I would qualify. And in fact, we don't. I mean, all of these, at each layer of understanding, we find that we know less. I think that's always been the case. The thing about the 4% and the 25% and the 70-something percent, we don't know what they are at all. But the measurements now of those quantities are pretty firm. So it's more than just something out there. We know that there is a certain category of properties which the stuff which makes up those components must have. It's not just any old thing. But we don't know what they are.
Thank you. I think in fairness, there are a number of people who'd like to ask questions. I'd like to let everyone have a go. Geoff, I tried to assign you a machine to put the program up there. The gentleman here in the blue jumper.
How much does the cosmological constant contribute to the acceleration of the universe? And how much is that related to the partial explanation of the dark energy?
So the cosmological constant was a constant put into Einstein's equations of gravity decades ago. It was put in there because Einstein wanted a static universe, and without it, it would either have to. There was no way for the universe to remain static. When the data showed that the universe was expanding, that's when he made his famous statement. The expansion of the universe is consistent with just that extra constant. But that doesn't explain anything. It's a constant put in by hand. That's a mathematical description of whatever physics or process has to be. It has to follow that, something like that. But it doesn't explain it.
The young chap on the back there.
If these black holes are singularities, then how can Hawking radiation dissipate these singularities?
Yeah, it's a quantum process. So what happens is pair creation occurs. The vacuum can, just like photons can create electron-positron pairs. Well, at the edge of the black hole, where there is, especially on small black holes, where there is a strong change in gravity from this point to that, you actually have a tension. You can pull particle-antiparticle pairs out of the vacuum. One goes into the black hole, and the other one is ejected to infinity. So that's where the energy losses occur.
The gentleman here in the hat's been waiting for what?
I'm very glad, Professor. You said earlier that the photons can't penetrate plasma. I thought with the photon as mass must be charged, as you explained. Then simply why can't it penetrate plasma?
A little bit as a skin effect, but the charged particles interact through photons. So the fact that this gas is totally charged means that the photon will end up scattering through Compton scattering and others. So it just interacts. So it just doesn't penetrate. Whereas when the gas becomes neutral, the effective charge is shielded because you have an electron and a proton, so a neutral object, and the photons can penetrate much more.
So it's a great pleasure to see my head of department being asked these very curly questions. I appreciate it very much. I think I've given the lateness of the hour. I'd like to call for one final question, and then if you've got some pressing questions, please come down. I'm sure Geoff will stay for a few minutes. Our last question, the gentleman up the back.
What I want to ask is what kind of matter is are expecting to be created with the next phase of particle physics, which is what we're doing at CERN, and at what stage of the universe does this matter mimic what of the universe, what time frame of the universe after the Big Bang does it mimic?
10 to the minus 12 seconds, approximately, after the Big Bang. So a million minutes per second. And the sorts of materials that will be created in most of the events will be made up of those particles I talked about at the beginning. But there is so much energy available that with low probability, and that's why it's so hard, because we have to dig them out, with low probability there will be some very heavy particles created. And we're hoping that by pulling out some of those heavy particles and trying to understand what they are, whether they'll be mini black holes, or whether they'll be Higgs bosons, or whether they'll be supersymmetric particles, or whether they'll be this or that, that's where the fun and games start.
Okay, well, the fun and games may start at that point, but I'll have to draw tonight's lecture to an end. I'll just remind you again about the other three lectures we've got to follow on successive